It's okay.
Cool. So it started.
I'll just actually, since it's recording now, I'll actually say the things. It's we
Yeah,
are
I'd introduce you. Let me do that.
okay.
Right. Uh, so Rajdeep is a first year student at CMI. He was also actively involved in Olympiads, and he was preparing for Olympiads, and he also did JE. He's quite excited about mathematics as well.
Yeah.
Sorry, what did I mess up?
No, that's actually completely fine. I did Olympiads and I went through JE, and I like math. That's okay. It's more than what I was saying in the beginning. Uh,
Alright, sorry to disturb you. Go on.
no, it's okay. It's okay. Right. So, thank you, Ron, for that introduction. The recording started a little late, I think 15 minutes late. So, I'll actually go over the things I said before. Uh, I was trying to tell the people here what a symmetry is. And we started off defining, and we started exploring the more colloquial picture of symmetry, which is that it's a it's about mirror flips, and it's a property of the object that under a mirror flip about some axis of the object, it stays the same. Then we expanded that definition to allow for more different kinds of symmetries. Right here. Things like rotational symmetries and translational symmetries. And there's more stuff. There's temporal symmetries and God knows what, spatial symmetries and all that. Where there is obviously some symmetry here, right? For example, if you took a square and you rotated it by 90 degrees, it is the same fundamentally. You could say that if I say 1, 2, 3, 4, these are the vertices of the square. If I rotate it, every vertex is displaced. How is it the same? It is the same, but if you just relabeled 1, 2, 3, 4 as 2, 3, 4, 1, now it's the same, right? So it's just a relabeling, but fundamentally it's the same. So we wanted to expand our definition of a symmetry to something that would allow for these different kinds of symmetries and not just a mirror flip. And which is where we defined a symmetry of an object O. We haven't defined what an object is, we'll come to that. As a structure preserving bijection from O to itself. I also quickly went over why bijection from an object to itself. Here object, I'm using it equivalently with set, but the bijection from a set to itself is just a permutation of that set. Again, I also stress on how permutation is it's a finite phenomena where you can only say something is a permutation of a something if the something involved is finite. You cannot talk about infinite permutations. Or maybe you can, but it won't make much sense. So a permutation or just a relabeling of your set. That's what a bijection from a set to itself is. And now we were talking about what structure is. And that's where I think we started recording. Right. So now that we're up to speed, right? I was just saying that structure is something that you impose on a set or you equip a set with. There's lots of ways to phrase this, and basically, a structure is on a set is just a language in which two elements of the set might talk to each other. Sometimes it's a binary operation on the set, right? And then we realized that this is a very vague and wordy definition, so we went on to the example of the set of integers. Z equals -3, -2, minus, and like the whole thing, minus infinity to infinity, and it's infinite, and and contains the integers, right? So and then we realized that the set of integers is not just the elements of the set, that it's not just a discrete infinite collection of objects. It's so much more than that, and we all know it. And that's where I think we start recording, and so now I can go on. Z is so much more than just its elements. This is one of those the sum of the parts is not the whole thing. So what makes Z more than just its elements? Well, for starters, there is an addition operation defined on Z, right? We can add two things, and we can and that addition has its own set of nice properties that it satisfies, right? There's also multiplication between two things. We can multiply two numbers to get a new one, and also addition and multiplications themselves mesh to do nice things as a distributive property. There's so much going on here that makes Z so much more than just the numbers that constitute it. So this is the thing. The things that make Z more than just an infinite discrete set is called the structure of it. So I feel like now the whole idea of the language of the set, so that's clear. I think some of you might complain that this is still fairly vague, and because it is, the language in which the elements of a set might talk to each other can be incredible. That's an incredibly diverse category, right? There's so many ways the elements of two set can talk to each other. This is why it's vague. If something is too broad, it has to be vague. Like if a definition is too broad, it has to be vague. So yeah, so that's what structure usually means. By an object, by an object is just set with imposed structure. With imposed structure. So Z, in that way, Z is an object. It's a set and more. And by and more, I mean there's a language in which the elements of the set talk to each other with imposed structure. So that's what structure and objects mean. So now that we have a somewhat self-contained definition of a symmetry, let's actually get what it is. We already went through why a symmetry is a permutation, right? We already went through why a symmetry is a permutation. It's not just any permutation though. It's a structure-preserving permutation. A structure-preserving permutation, by the sounds of it, is a permutation that respects, it is compatible with the language of the object, with the structure of the object. So, yeah, that's basically what it is. A symmetry is a permutation of the elements of the set so that if two elements talk to each other a certain way before the map, then images will have to talk to each other in the same way. Again, this is very vague, so let's come to examples. Look at this square, right? Look at this square. One, as I said, one would make the mistake after what I've said, that one would mistake this for a simple collection of 4 points. There's a lot of things that are going on here, right? For example, there's adjacency involved, that it's just not a loose collection of red, blue, green, and yellow. The red and yellow are connected, and the yellow and blue are not connected. So this is the structure of this set. The structure, the language here is adjacency, where the two vertices are adjacent or not. And if you wanted to find the symmetries of such a thing, that symmetry would be a permutation which respects this fact. So that if two elements are adjacent initially, then they're mappings. So if whatever the map of red is, and whatever the image of red is, and whatever the image of blue is, they have to be also adjacent, right? So let's try to. So for example, if you look at this map, you send red to blue, blue to green, green to yellow, and yellow to red. This is clearly a rotation. We're just taking a 90-degree rotation, right? Is this a permutation? Yes, it is, right? We just took red, blue, green, yellow, and we permuted it to yellow, red, blue, green. The permutation of the 4 vertices. Is it also structure preserving? Yes. And why wouldn't it? If two things are adjacent and I move them both, then they're still adjacent. This qualifies as a symmetry. So it's not just any permutation, it's a special kind of permutation which preserves this nice language on the set, on the object. Now, if you look at this transformation where you send red to green, green to yellow, yellow to red, and blue you just map to itself. This is not a symmetry. Mainly because initially blue and green were adjacent, right? They're adjacent, they're connected by an edge. But the image of blue is blue, the image of green is yellow, which are not adjacent. So this permutation of the vertices it's not respecting the adjacent language of adjacency that we've defined here. So that's what a symmetry is. And that's what, well, mathematicians call a symmetry. So now we can actually ask a very important question, which is, okay, so Pranav has said something. Thank God I'm on the chat. Even if we won't label the vertices, say we send sides, then diagonal side won't make it symmetric, right?
I mean length of diagonal greater than length of side. So
yeah.
Fit, right?
So now we're talking about even more structure. Now you're talking not just about adjacency. You're also saying that there's lengths involved. That's even more structure. So the lower transformation is not a symmetry, rather spectacularly. Like it doesn't qualify as a symmetry on too many things. So yes, thank you for that, Pranav. Thank you for that. Right. So okay, any questions at this point? Cool. So at this point, if I gave you an object, any object, right? You could ask me a very important question, which is, what are all the symmetries of this object? And the task might seem very daunting at first. I mean, you have an object and it can be symmetric in so many ways, because symmetry itself is a very elusive idea, right? It can be so many things. It can be flips and rotations and translations and God knows what. So asking the question of what are all the symmetries of an object is a tough one. And that's exactly what a group is. So if you ask the question, what are all the symmetries of an object, that is exactly what a group is. A group is just the set of all symmetries of an object. So if you give me an object, I can give you its resulting group, which will be the set of all its symmetries, all, exhaustively, all its symmetries, right? And yeah, so this is and obviously when I did group theory first, I had that vague abstract definition of groups, and it was annoying. But when I found this for the first time, I was like, okay, something concrete. And so all of you would agree with me, this is fairly concrete. There is no weird abstraction and binary operations and random sets and all. It's a fairly concrete thing. You give me an object, and in return, I'll give you the set of all its symmetries. A quick remark at this point, that what I said before, the task of finding all the symmetries of an object seems rather daunting, because yes, it can be symmetric in so many ways, oh my god. But remember that at its heart, a symmetry is just a bisection. I mean, it's not just a bisection, it's a lot more than just a bisection, but it's at least a bisection. And the set of bisections itself it's finite, for a finite set, that is. If you have a finite set of n objects, there's n factorial bisections on it. Does everyone follow that? If I have 1, 2, 3 for n. Okay, I think I should actually quickly do this. Okay, I'll clear the frame. Okay. Right. If I have, right, so number of bisections from a
I
finite.
guess like where you are writing is not visible. The Jamboard is like.
I'm so sorry. I'm so
Scroll
sorry.
down.
Yeah, okay.
Yeah, no, it's
Number of bisections from a set of size n is n factorial. Yeah, this is kind of a baby problem, but can someone quickly tell me why this is true?
Due to
It's
the
just number of
permutations.
permutations.
Yeah. So a bisection from a set to itself is just a permutation, and the number of permutations is n factorial. Why? If you have n objects, you map 1 to something, and 2 cannot go there. So it has n minus 1 choices. So 1 has n choices, 2 has n minus 1 choices, and so on. So that's n into n minus 1 into n minus 2 up to 1, which is n factorial. The number of bisections itself from a finite set, it's bounded, and it's not infinite. It's not a small number, but it's definitely a fixed number. The set of symmetry, which is a subset of the set of bisections, has to be also finite, right? Right. Any questions at this point? Any questions with this definition? Great. Right. So let's just.
I don't know if you will cover it further though. But like if we talk about group 0, 1, 2, 3, 4 are the elements, and like the function is addition mod 5. So like what will you classify as symmetry here? Like you say group is a collection of symmetries, all the symmetries. So what are the symmetries here?
So you're asking. So the object you're giving me is 0, 1, 2, 3, 4 modulo 5, and you're asking me for all its symmetries.
Yeah.
It's the the funny thing. It's just the set 0, 1, 2, 3, 4 modulo 5. Where when I say 0 mod 5, it means shifting. So if you write 0, 1, 2, 3, 4, you add all of them by 0. Similarly, if I mean the symmetry 1 mod 5, you shift all of them by 1 mod 5. I didn't put this example specifically because there's a lot of background theory here. But yes, Z mod 5Z, the group of this set is just the set Z mod 5Z. I'll take a more large example of this later. So yeah. Is that okay?
Yeah, fine, sure. Fine.
Great. Uh, okay, I'll actually have to go for just 1 second if you all can excuse me. Please don't leave. Just 1 minute and I'll come back. Thank you so much. I'll just let you guys look at this. Don't know how. Yeah. All right. I'll come back in a while. Right. Hi everyone. Sorry for that. Right. So now that we've defined a group the way we have, it's a good place. This is a good place to just look at examples because there's really nothing more left to explore here, right? I mean, we defined a symmetry and we defined a group that only depends on the definition of symmetry. So we can just look at examples now. Nothing is stopping us. Right. So we already defined an object initially. This object, right? This square with the red, blue, green, yellow vertices. You could ask me, well, this is an object. What is the set of symmetries here? Okay, this is more. Okay, Chirag is saying since the number of variations. No. Exactly, Pran. If your set is finite, if your object is finite, then the group is definitely finite. Absolutely. But if your object only is infinite, you can't really say that the set is that the group corresponding to that object will be finite. But yes, if your object is finite, which is actually what I wrote here in the remark. Okay. Yeah. Finite objects correspond to finite groups. So yeah. Thank you for. Yeah, it's okay. Fair thing. Right. So we would like to go back to the square, right? This is the square. And okay, so any guesses on. So I'm not even asking for the full set of symmetries, just some symmetries of this set. We've already talked about one, right? This is the symmetry of the square. Any other?
Like if you rotate it 2 times, then also it's a
Exactly.
symmetry.
Reflect in the y-axis. So, you mean like this, right? So, sorry, I can't. I have to do it on Jamboard and it won't come out as pretty.
Oh
But
yeah. I mean, like vertical. So
yeah. So like flip like this, right? It's a good, that's a symmetry, definitely. For those of you who don't believe, Chirag, that this is a symmetry, check for yourself. This is in fact a permutation, and that if two things were adjacent to begin with, their images will be the same. That if you have a horizontal edge, it will just flip on its own, and so adjacency is maintained. If you have a vertical edge, it will just go like this, and adjacency is maintained. So yes, mirror flips are definitely um, a symmetry about the y-axis, and by
And
that
like,
we.
yeah.
Pranav?
Yes, I was saying like the other symmetry can like just interchange red and green vertices.
Sorry, I couldn't wait.
The other symmetries can like interchange the red and green vertices.
interchange the red and green. Exactly. So that's what is that? That's a symmetry about the blue yellow line, right?
Yeah.
The symmetry about the blue yellow line. This line. Sorry, that's a mirror flip about the blue yellow line. So yeah, that's also symmetry. And since we've already talked about the y-axis reflection, clearly the x-axis reflection works also. And Pranav also pointed out the blue-yellow flip. So we take this axis, the line passing through the blue and yellow points. We take that as an axis and we take a mirror flip. That is also symmetry. You can check that it qualifies all the conditions. If blue-yellow works, what's stopping green-red? So flipping yellow and blue. So we exchange them. That is also symmetry. So, okay, Pranav also pointed out that two rotations, so 190-degree clockwise, another 90-degree clockwise, so that's a 180-degree clockwise rotation. That is also symmetry. Why? And this highlights a bigger point that if F is a symmetry of your object and G is also a symmetry of your object, then F composed with G, and I can talk about compositions because well, they're functions. F composed with G is also a symmetry. Why? Because if G is a structure preserving bijection, it means it preserves the ending product has the same structure as your starting. So okay, so you have your object O, G takes O, spits out O again. So that O now has the same structure it had before, and it's also the same set. Then you apply F to it, the same thing holds. So F composed with G is structure preserving, and it's a bijection from the set to itself. This highlights a larger point that if I compose two symmetries, the resulting function is also a symmetry. Great. Uh, can someone point out another one? So okay, so let's go over all the things we've covered. We've covered every possible mirror flip. We've talked about the vertical mirror flip, the horizontal mirror flip, and the two diagonal mirror flips. So that's four symmetries. Um, we've also covered right. So it's kind of sad I didn't say it earlier. There's also the most dumb possible symmetry. Can we move this? No, because your codomain is the square itself. This is fixed. So you're okay, you can only map red to either green, yellow, or blue. Yeah, no, translation is not allowed. Because if you wanted to allow it, you'll have to extend it to R square instead of just the square. You want to stay in this subset. So translation and all that business is not allowed. Yeah. So there's the dumbest symmetry that no one of that somehow I didn't talk about. It's the do nothing symmetry. Just do nothing, which is what we call the identity symmetry. Just map every element to itself. If you include translation, there will be infinite, right? Yeah. If you include translation, just move it somewhere. It's the same. Yeah. Anyway, so the identity symmetry. Map red to red, blue to blue, green to green, yellow to yellow. That's a symmetry. It's clearly a bijection from the set to itself. And adjacency is also clearly maintained. We didn't even change anything. So there's the stupid do nothing symmetry, which we call the identity symmetry because it doesn't do anything. Then there's a single clockwise rotation. Then there's clockwise rotation composed on itself. What is stopping us from doing it three times? So there's 190-degree rotation clockwise, then a 180, and then a 270. You could say, let's keep going. Let's just do it four times. But if you rotate a square four times 90 degrees, then you're just getting the same thing back. So that the rotating the square four times 90 degrees has the same effect as the identity. So you've not found a new I don't get Chirag's question. He's saying if we consider each rotation differently. So
I
like
mean, if we like rotated, for example, say 20 degrees to the
oh no.
right,
Then you're not staying on the square, no. Then you're going to some other place.
I mean,
Then
like
again
if
you
you
have to
rotate the
extend.
entire square, I see.
Yeah. But then you're not staying on the 4 points you have to stay in, right? And you're going to a different point in the plane.
Oh,
Your
okay.
red can only go to green, blue, and yellow. That's all its possible range is. Vishwab is here. I think my net is suffering a little bit. Can everyone hear me properly?
Yeah, you're
Yeah.
audible.
Yeah.
Okay. For a second, things sort of froze up. Anyway, right. So we found the identity symmetry, a single 90-degree rotation clockwise, a 290-degree rotation, that is a 180-degree clockwise rotation, a 270-degree clockwise rotation, and we stopped because After that, you just back to the identity. You could also ask, what about counterclockwise rotation? So counterclockwise 90-degree rotation has the same effect as a clockwise 270-degree rotation. Convince yourself of this. I don't know how clear it is, but if you really think about it, they have the same effect. Like the mapping is the same. But under that 270-degree clockwise rotation, red will go to yellow, and then blue will go to red, and so on. The same holds for a 90-degree counterclockwise rotation, where red will go to yellow, yellow will go to green, and so on. So that's convinced, right? So we also found a new thing, that if f is a symmetry of your object, there is another symmetry, f inverse, that reverses the effect of your symmetry, right? So that's nice. So okay, so let's count. We have the identity symmetry, that's 1. We have the simple 90-degree rotation, that's 2. 180-degree, 3. 270-degree, 4. Then we have the 4 flips that we found. 5 is the horizontal flip, 6 is the vertical flip, 7, 8 are the diagonal flips, right?
Oh yeah, we can also find like clockwise rotation with a diagonal flip composed.
Exactly. If you try to do that, you'll realize that it's the same thing as a diagonal flip. Think about it. You rotate and then you do a vertical flip. That's the same thing as doing a diagonal flip. I
No,
think
I mean rotate and then a diagonal flip. Like then the red comes to the blue point, the blue point goes to the red point, and the green point goes to the yellow point, and the yellow point goes to the green point.
uh, listen. This is a little tough. Okay, I'll tell you what. You're limited to just 24 choices, right? Just of all the possible permutations, that's just 24 of them. You can just check which of these is actually qualifies as a symmetry. So you have 24 choices. Sit and try which of these actually qualify as a symmetry. You'll see that you're actually just stuck with 8 things.
Oh,
I'm not
sure.
saying that, like, I'm not saying I'm going to do it, but if you really want to, you can actually say that the eight symmetries that we found are the only ones. Any other combination will actually be, well, uh, one of these.
Yeah, sure.
Here, okay, so I want to draw your attention to something, which is that if you, so the thing that I just said, that your choices of symmetries of the square is limited by the choices of bijections you have. So you have 24 choices total. I claim that the set of bijections from just a discrete set, right? Just a set without any structure is a symmetry as well. Like it's a set of symmetries as well. Okay, this got a little vague. Let me do this on the Jamboard. Oh my god. Oh, it's almost 7. I have to stop at 7:30. Wow, I have to cover a lot of things. Uh, right, what was I trying to do? Right. So initially we started off with, I'm actually not going to do the red, green, blue, yellow thing. Let's call it RBGY. Okay, wait. Yeah. Say there were no edges. Just saying. There was no structure. Just saying. This is just wishful thinking, okay? See, there was no structure. These were just 4 points lying around, doing nothing. And you asked me, this is the object I'm giving you. What are the set of symmetries it has? Since there is no structure here, any permutation of these 4 points is a symmetry. Because you see that this is what we call the trivial structure, if you want to call it that. That a structure preserving bijection from a set that has no structure means that any bijection qualifies. There's no cutoff. Any bijection is a structure preserving bijection because there's no structure to preserve only. Right? So you could, and here I don't need to write them suggestively in a square form. You could just have RBGY in any order. And you just look at all possible permutations. Right?
Like the rotated by any angle, that also works here, no? For
Yeah.
infinite.
No. Because first of all, rotation as a concept only fails. Secondly, you're still limited to uh, the same set, right? R can still only go to B, G, and Y.
Or didn't you say that there are no sides? Like the structure.
Fine, but your range is still fixed. Like you can only, like remember what a symmetry is. It's a bijection from the set to itself. You can only map R to either one of R, B, G, Y. You cannot do it to any other point, right? It's just that now there's no restrictions. You can map R, B, G, Y to any permutation of it,
Oh,
right?
okay, there are no connections, right?
There are no connections. There's nothing stopping you. There's nothing stopping any random bijection from being a symmetry.
Yeah.
This is what. So then, in that case, the set of all symmetries of an unstructured set. So if your set has no structure imposed on it, and if you wanted to say, okay, what are all the symmetries here? Any bijection will qualify. So any permutation will qualify. Set of all symmetries of an unstructured set, finite set. Let's just stay on fine. Unstructured finite set, finite uh, set, set. Okay, right. Set is just the set of all bijections. So there's the set of all bijections. I didn't write any of this. Set of all symmetries is just the set of all bijections. Now, what is the set of all? Like, what is the size of that set? 24, right? 4 factorial. This is what we call the symmetric group. The symmetric group Sn. Symmetric group of sorry. The symmetric group of size n. This is also called the permutation group of size n, right? So yeah, we've just found another group. If there is no structure to preserve, then any bijection qualifies, and hence, in that case, any permutation will work. And so now you have a new group. If your object has just n elements and no structure, then Sn, this S subscript n, is the set of all symmetries of it. Great. A last example, Z. Coming back to Z, right? I'll zoom out actually. Yeah. I'll clear the frame. Clear the frame. For the last example of a group in this language, look at Z. The set, the object Z. Dot, 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 -3, -2, -1, 0, 1, 2, and 3, and so on. This is your object. Can someone tell me what? Okay, so this is actually kind of vague. Actually, no, let's just stay here. Can someone tell me, when you know the structure on Z, for now, just consider addition. Can someone tell me a symmetry of Z? Remember, the symmetry is just a it's a relabeling. Can someone tell me a symmetry of Z?
Adding something like.
Exactly. So now adding, okay, definitely adding works. So plus I. Let plus I be the symmetry or the function which maps every element A to A plus I. Say you look at the symmetry 2, just plus 2. Then this sends 0 to 2, 1 to 3, and so on. It sends -1 to the 1. It sends -2 to 0, and so on. Why is this a symmetry? Someone tell me. Because it preserves the additive structure of Z. That if 1 and 2 add to 3, then the image of 1 and the image of 2 will add to the image of 3. And you can see that plus I, where I is any integer, including negative, is a symmetry of Z. I don't want to say that. Yes, it is a linear map, but no jargon, please. Yeah, but yes, Chirag, it is a linear map. So, surprisingly, weird turn of events, the set of symmetries, the group corresponding to Z is Z. It's kind of a fun thing that happened here. Also notice that all the things that we thought of before, the whole thing with compositions and zero and like the identity symmetry and inverse symmetries, all of these are true. So there is a identity symmetry, which is addition by 0. You shift the whole thing by 0, nothing changes, and still is symmetry. So that's the identity symmetry. If plus I shifts everything forward by I, then minus I will put it all back. So the inverse symmetry of plus I is minus I. And you can compose two symmetries. You can compose plus I and plus j to get I plus j. right? So yeah, so we've not right. So these were some examples of symmetries. Any questions at this point? Okay. So we've noticed something. We've noticed that if G, if a group G is the set of all symmetries of an object, then the following three things hold. One, it probably zoom in a little bit, just a little bit. Yeah. One, there is a zero symmetry. There is a do nothing symmetry. What? I'm sorry. Just give me a second. My tab hand, right? There is a zero symmetry, so as to say. We also call this as 1 or E sometimes, depending on the kind of structure there is on the object. It is a zero, but keep in your mind that this just refers to the do nothing symmetry. It's not doing anything. Also, what is true for any set of symmetries is that if G1 is a symmetry, G1 is a symmetry, G2 is a symmetry, then if I compose G1 and G2, G1, G2 is also a symmetry. We saw this multiple times. And hence G1 composed with G2 lies in G. So if G was your initial group, capital G, then if G1 is in G1 is in G, G2 is in G, then G1 composed with G2 is in G. Right? It's also a symmetry. Lastly, if G is a symmetry, there exists a G inverse element of okay.
I have one doubt.
Yeah.
In like the Z plus I symmetry, the structure is not completely preserved. Like, okay,
No,
we
I'm not
can,
talking about multiplication. No, multiplication is
not
we're ignoring.
multiplication. In addition only, like let's take 1 and 0. So 1 plus 0 should be 1. So image of 1 plus image of 0 should be equal to image of 1, right?
Hmm.
But like if you add by 2, it will make 3 plus 2 equal to 2, which is not true.
Oh. Okay, so it is 0 and 1. The image of 0 is 2, then 3. 1. Okay. Hmm. This backfired terribly. Yes, Pranav, you're right. I did not think this through. So just ignore the Z example then. We went through two examples, which is the dihedral group of order 2n. Oh, I didn't actually describe the dihedral group of order 2n. Let's just do it. Right. So what we saw was a more specific example of a general thing. We saw a square, right? We were talking about the symmetries of a square. If instead of a square you just had a regular n-gon, right? Just a pentagon or a hexagon or just a regular n-gon, then you could ask me what are all the symmetries of that object. And the answer to that question would be the dihedral group of order 2n. Order is it's a technical word for size when it comes to groups. So that's what D2n means. It's we got the dihedral group of order 2n. And its elements are exactly what you would expect, like after you come back from the square, right? There's 1, which is the do nothing symmetry. There's R, the clockwise rotation symmetry. There's R square composed again and again. And since it's n, after you do n rotations, if you come back to the original, then there's all the flips. So there's just a general flip about the vertical axis, and you rotate it and then you flip. So that's a flip about some other axis. And yes, like if you really look at it exhaustively, you'll see that this is in fact the set of all symmetries of the S. So this what I've written here is this R squared thing. there's some notation here that I should explain. R refers to the clockwise 2 pi by n degree rotation. Okay, that's what R refers to. R squared means R composed with R. That's so composition, multiplication represents composition. Multiplication represents composition. S represents the mirror flip about the vertical axis. And so you have these relations, which is r to the power n is 1. It just means that if you rotate the regular n-gon by 2 pi by n, like with an angle of 2 pi by n times, then you're just going to get the original back. That's what r to the power n equals 1 means. S square equals 1 means you flip it once, you flip it again, you'll get it back. You'll get your original back. Rs equals SR inverse, where R inverse where R inverse represents the inverse symmetry of a single 90-degree rotation. So that's a counterclockwise 90-degree rotation. This relation holds. Rs equals SR inverse. Why exactly, you'll have to draw it by hand and check. But yeah, this is holds. And you can, if you try to do this, like if you try to think of all the ways you can compose R and S, these three conditions will limit you to just D to N. So yeah, that's what the dihedral group means. We've seen two examples, and from these two examples we try to extract some information about general groups in general, right? So we were writing how if G is a symmetry, then G inverse there exists a symmetry G inverse in G, such that if you compose G and G inverse, then you'll just get the identity map. Right. You just get the identity map. This is the same thing as the existence of R inverse in a dihedral group. You rotate it clockwise by some angle, rotating back counterclockwise will give you the identity map. So that's what it means. So these three properties hold for any group. There is a zero sign, the do nothing symmetry. You can compose symmetries and it will still be a symmetry. And there's an inverse symmetry. So now this is where what it leads. This is where it leads us to the classical definition of a group. And I've written TM, it is a trademark, in the sense that this is a definition you'll find everywhere. And I've just written out the same thing I just said. These three properties hold. So now this means that okay. I think Rohan left, because of which if people come, then I'll have to let them. It's okay. Right. So what we realize now after seeing that any group has these three properties is that the group is just not a set. It itself has structure. You can compose two things and you'll get the same thing. There's structure on a group itself. So you can ask another question. Is if I give you an object, and by which I mean a structured set, a set with some structure, can you tell me whether it is a group of some object or not? That's a question you can ask, right? So now we'll have to answer that question. Well, if your object, your structured set, was a group, then it had to satisfy the three properties that I just wrote. That had to have that if your object was a group, it would have an identity element, whatever that means. Which means that if the identity element is such an element, which I mean that if you compose it with any other symmetry, you'll get the same symmetry. So G composed with 1, so any symmetry composed with the identity symmetry is just the symmetry. So it's just G. So that's what the identity means. Composition is allowed, which means there has to be a binary. Composition is just a binary operation, right? So if your object was in fact a group, then it had to have a binary operation, which would be representative of group composition, of symmetry composition. It had to have an identity element where the binary operation, actually I'll just show the definition here. See that all these properties, that a group an object which had all these properties has a good chance of being a group, right? It has an identity, and the identity behaves with respect to the binary operation in the exact same way you would expect it to. It would have associativity, which is something that stems directly from the fact that this binary operation is representative of function composition. That function composition is by definition associative. That f of g of h is f of g of h also f of g of h. So function composition is associative by definition, and so any object, any structured set, that the structure of that set had to satisfy these properties. That's how we. So now we define a group, and actually we redefine a group because we already defined a group as a set of all symmetries of some object, but now we are redefining it. Okay, to be a set, and binary operation on that set which satisfies these properties. So there is an identity element such that 1g, and when I say binary operation, I usually treat this as multiplication, but it doesn't mean it's just multiplication. It just means binary operation. And I can't say 1 star g. It's kind of wordy. So I'll just say 1g times g, and then is equal to g times 1g is equal to g. This reminds us of the fact that there is an identity symmetry. It doesn't change anything. There's also the binary operation is associative, which reminds us of the fact that function composition is associative. There's also the inverse. Any element in your group, in your set, has to have an inverse with respect to the binary operation. And so this is the redefinition of a group. This is where we come at par, come on board with the more well-known definition of a group. So also note that we didn't write down the fact that composition is actually like closed, like your because we found out initially that we can compose two symmetries to get a new one, which in this definition would correspond to saying that g1 multiplied by g2 is still in g. But we don't need to do that because the binary operation is defined from g cross g to g. I don't think I've written it down, but that's what a binary operation on g means. It means g cross g to g. Which is I take two elements and I spit out an element in g. So closure holds by definition of star. We also added a new condition of associativity, which again, as I said, shouldn't be too hard to believe since function composition is associative. This is where we realize that now we have two sort of things here. We started off defining groups as a set of all symmetries of some object, and now we've defined groups as this weird abstract thing. Why should they be the same? Right? Why is there any equivalence between these two things? Note that you can actually look at the set of all symmetries of an object as a group. And from now on, when I say group, I mean this abstract, weird thing. From now on, I don't have a lot of time. The goal of this talk, as of now, is just this. That the way I have defined a group as a set and a binary operation on it is actually the same as the symmetry definition of a group. See that one side of this argument is clear, that if you have a set that is a set of symmetries of some object, it has these properties where the binary operation is function composition, right? Say you have a set of symmetries. Okay, I'll share here. I'll clear. That if S was the set of all symmetries, no longer using the tab somehow. But if S was the set G1, G2, and so on, up to Gn, where all of these are symmetries, then the binary operation I can define on S cross S to S, is just function composition. That G1 star G2 is just G1 composed with G2, right? We define this. This is how we define the group corresponding to this set of symmetries. And you can check that all the things that the definition of a group demands, these are all satisfied by function composition, right? So we proved this one thing, which is that any set of symmetries, the set of symmetries of any object, is in fact a group. And by a group, I mean this. That any set of symmetries satisfies these properties if you modify it a little bit. The other way is saying that if you have a group, if you have a pair G star, where G is a set and star is a binary operation on it, if you have this kind of weird abstract object, then this is the set of all symmetries of some object. That is the claim. Since we want to show that the two definitions of group that we've defined till now, they're the same. We want this sort of equivalence between the two definitions. One way is clear, but the symmetry definition implies this weird abstract definition, because all of these properties on star that we define, we borrowed them from function composition, right? We built this definition of a group to answer the question, when is an object the set of all symmetries? Now you have to go backwards. We're just saying that if I have a weird looking mathematical object, is it always the set of symmetries of something? And that's when group action and Cayley's theorem comes in. So I just said a lot of things. Any questions at this point? Okay, that means I either did a really good job or a really bad job. Okay. I will not need this anymore. And here, frame. Right. Okay. So the goal now is this. Goal. The weird abstract definition of a group with the whole set and binary operation of a group implies that this object, that this group, and I've said this in parentheses because we're using the new definition, weird abstract definition of the group, is actually the set of symmetries of something, of an object. This is the goal. And this is exactly what Cayley's theorem states. A group G is a set of symmetries of some object. This is what Cayley's theorem says. Now, if you look up what Cayley's theorem is, it will be a little different. I claim, and I will show, that in fact the Cayley's theorem that you will find, actually I think I can just Google it now. Wikipedia. Right. If you come here, it says that every group G, and by every group they usually mean a finite group, but every finite group G, and here when they say group, they mean the weird abstract definition. Every finite group G is isomorphic to a subgroup of the symmetric group acting on G. This is a lot of words and a lot of jargon, but I will actually show this is a weaker version, that it's actually a corollary of this version of Cayley's theorem. Sorry. Wait. Tab. Okay. Yeah. So this is what we'll try to show. Okay, so before anything happens, I'll actually like to add on something. And this is something that's very nice. And this actually leads to this weird definition of a Cayley's theorem. The weaker version of Cayley's theorem. Say you have a finite object of size n. Okay? Your object is finite and it is of size n. Say there is no structure on it. There's nothing. The elements of this set don't talk to each other. Right? What is the set of symmetries in that case? Anyone?
Any permutation?
Exactly. Any permutation. So it's the permutation group, S subscript n. Right? So in that case, when there is no structure on the group, on the set, on the finite object, then in that case, the corresponding group is S subscript n, right? This is the simple scenario. There is no structure, you don't have anything to worry about, any permutation works. Say instead, there was some structure imposed on the group. It was that the elements and the no structure is also structure, non-trivial structure on the object. Then you'll see, then do you realize that not every permutation as of now qualifies as a symmetry? That some permutations will not preserve the symmetry, will not preserve the structure of the object. We saw this, right? This transformation of the square, it's a permutation of the vertices, but it's not a symmetry. So this is what happens when you dump structure on an object. It cuts off certain permutations from being symmetries. Now you're looking at a subset of all the symmetries, of all the permutations of these n objects. So the whole point of this is that if you have a finite object with n elements, if it has some structure in it, it will be a subset of the set of all permutations. Do you guys get what I mean? And this is actually the weak version of Cayley's theorem. Cayley's theorem says that if you have a finite group of size n, then it is the same as a subset of the set of all permutations. And there's a subgroup of Sn. We'll define what a subgroup is hopefully later. For now, it just means a subset of the set of all permutations. And that makes sense, right? If I constrict my object, if I add more structure to it, not every permutation will qualify, only some of them will. And so only a subset of the set of all permutations will qualify as a symmetry. So any group which corresponds to an object of size n is a subset of the set of all permutations of size n. This is exactly what Cayley's theorem is. Now think about what would happen if I introduced groups in that weird, in this fashion, that it was just a pair G and star, where star is a binary operation. Cayley's theorem would seem very arbitrary. It would not make any sense. I mean, you could see a proof and you're like, okay, fine, the proof works, but why? The why here is clear. I added more structure, so my set of possible permutations that satisfy structure preserving condition drop, and that's why it's a subset. So yeah, that is it. That's something I wanted to point at. Actually running out of time. Oh, this is kind of sad. I had a lot to do actually. But I think this is where I'll have to close, I have to stop, because it's 7:30 and yeah, it's about time. So I think that is it. I will, however, leave you guys with something. This theorem. The group G is a set of all symmetries of some object. All symmetries. So if you have a group, if you have an object that satisfies these properties, it will you can in fact construct an object such that the set of all symmetries of this object will be exactly a group G. Now, I can only ask you guys to try out this by yourself because I've run out of time. Kind of sad. But yes, this is in fact true. And chances are, if you really try hard, you'll actually find a rigorous proof of the weak version of Cayley's theorem, that any group G is a subgroup of the symmetric group. We'll find that in the video. I will, since I've run out of time and I really want you guys to see what this is about, I will link a group theory playlist by Richard Borchers, who is like a legend, and I'll send this link to OMC server. You guys can watch his video on Cayley's theorem. Yes, on YouTube, obviously. You can watch his playlist, and you can especially watch the second lecture. It's called Cayley's theorem, and it is the whole video is just a proof of this. And it's like 18 to 20 minutes long, so it's a whole thing. He motivates it to a very good extent, right? And so yeah, please watch it. I'll send the link. Actually, I can send it right now. Yeah, so I really recommend all of you guys to watch this lecture.
Anything we can prove.
Okay. I encourage all of you to go through that video. and just make sure that this makes sense. So I have only achieved part of my goal, which was to motivate this very weird definition of a group that usually is what you'll start with. You take up any book on group theory. This is what you'll usually start with. This is not a personally, I think this is not a great definition of a group. I personally think that this is how we should start defining groups. And then slowly build up to why at all we come to this definition. So that was half of my goal, to show that, well, this is in fact the case, that this seemingly arbitrary definition of a group is not that arbitrary. It's a culmination of a lot of ideas. That we saw that things were symmetric, or very random things. That say the symmetry group of a set of symmetries of a Rubik's cube is equivalent to some other mathematical quantity. And so lots of mathematicians saw these things and they're like, okay, fine, I'll work with symmetries and I'll come up with as small a definition, which is abstract, of a group. Yeah, so this is, I hopefully managed to motivate this definition of group well enough. But I'll have to stop now because I've run out of time. Thank you, everyone. You've been a great audience.